Okay, so our next speaker is Einar Pius from University of Edinburgh.
Good day. I'm going to talk about some new classical and quantum hybrid quantum circuit, which could be used to accelerate some computations, giving a better performance than the corresponding classical circuits. So, since I assume that some of you don't know anything about quantum computing, I'm going to give a very basic introduction to it before I start introducing the actual circuit. So, first of all, quantum bits are the quantum analog to classical bits. In addition to 0 and 1, they can be in a superposition, where alpha and beta are complex numbers. And their outcome is given by probability of 0 being alpha norm squared and probability of 1 being beta norm squared. So these are the quantum analogs to classical bits. So we can use multiple qubits by using a tensor product. And we write them as shown on the slides. 2 qubits can have 4 possible states and the superposition of all of these. If we have n qubits, there will be 2 to the power of n possible states and the superposition of all of those. And if someone would like to describe this kind of system classically, it would require an exponential number of bits to describe all of the amplitudes. So this gives a hint why quantum computation is not easy to simulate in general. Now, not all of the quantum states can be represented as tensor products, and those which cannot are said to be entangled. And entanglement is believed to be necessary for interesting quantum algorithms. So, a simple example of two entangled qubits is the Bell state, where we see that the probability of measuring 0 or 1 on either of the qubits is exactly half. But if we measure one of the qubits 0, the other qubit has to be 0 also. And this is an important state since a while ago Bell showed that this correlation is stronger than possible classical. Now, computation is done by unitary evolution. And an operator is unitary if the application of its adjoint gives you identity. And we represent quantum computations as quantum circuits. This is the most popular model. So here qubits are represented as wires. Unitary operators are represented as gates, similarly to classical gates. The gates are applied sequentially from left to right, and gates acting on distinct qubits can be applied simultaneously. And the depth of the quantum circuit is the number of simultaneous steps needed to apply all of the gates. And the depth is the measure which we will use later on to describe the efficiency of our circuits. Now, very shortly about quantum algorithms. There is the class of classic algorithms solvable, the class of algorithms we do not know how to efficiently solve, NP. P is the solvable ones, and the quantum analog to P, the PQP, which is the class of algorithms that you can solve efficiently given a quantum computer. So quantum computing is interesting because we have some algorithms, like the Shor's factorizing algorithm, that is not known to be solved classically, but can be solved quantumly. And this is the polynomial time integer factorization. It has some generalizations. It can also be used to find discrete logarithms. And its importance is, one of the importance is that it would break some public key cryptosystems. Another well-known quantum algorithm is the Qubits search algorithm. It doesn't give you as good of a speedup as the short one. It gives you only a square root of an speedup, where classically only n queries is required. But compared to short, it might have some. It solves a more wider problem. It's a search from a database, which can be used as a sub-routine in many algorithms. And another one is the approximating of Jones polynomial, which for which there isn't even a NP approximation. And this is a problem which itself is sharply hard. And this also can be solved quantum. Now, the motivation for our work is to find some kind of small computational patterns that could be used to accelerate computations. It should be small. It could be used as a GPU or FPGA to accelerate many kinds of computations. And preferably widely used. So, yes. And another motivation is that quantum algorithms are difficult to implement. For example, the highest number of qubits entangled is 14, as Wolf mentioned earlier. And for example, for Shor's algorithm, the required number of qubits that would be useful for any practical purpose, it's quite high. For example, 500-bit integers in general can be factorized on average PCs. Not instantaneously, but given some reasonable time. Whereas quantumly, the largest number that has been factorized is 21, and that was last year. It's not even 21 bits, it's just 21. So it would be useful to find some kind of small computational patterns, preferably not as resource consuming, but also another desirable property would be that they wouldn't be meant for a specific algorithm. They would be something that you can just plug in on your existing algorithms to accelerate them. So the arithmetic operations are the natural choice, since they're used in every CPU. So what we worked on is the Multiply Accumulator, or simply just MAC. It performs this kind of simple operation. It adds x times y to a register, and it is usually implemented in hardware using a multiplier followed by an adder. And as of its applications, the most obvious application is the matrix multiplication, which is widely used in many scientific codes, and also digital signal processors, which have implemented in hardware hugely parallel MACs to speed up their processing power. So they're usually used in a sequence. And now let's consider the MAC of k-bit integers. we are interested in the depth of the whole computation after you applied all of them, n of them, to be precise. So addition can be done in constant depth if you would use a carry save adder. But multiplication requires log k computational steps. And so this gives a total depth of n times log k. So what we will construct is a quantum multiply adder where the unitary operators, the gates we apply, for each of these max step, take only constant time. It does use some ancillary qubits, and it uses some kind of initialization and finalization steps, giving a total depth of n plus log k compared to the classical n times log k. So, start by defining just the unitary operator we want to do. Then we decompose it into smaller gates, which we can actually hope to implement. And then make it parallel, make all of these gates act simultaneously. So we will use it on a quantum Fourier transform state. Well, the quantum Fourier transformation is similar to the discrete Fourier transformation, whereas the discrete Fourier transformation transforms complex vectors. The quantum Fourier transformation transforms quantum states. And although they are similar, a quantum Fourier transformation on n-qubit state will act on an exponential number of amplitudes. So it acts on a large error space. And you can only measure one of these values when you want to access information. The quantum Fourier transformed state, integer represented in a quantum state, can be written as shown, where we use the binary fractions and binary representation. And if we define a simple single qubit operator for the QMAC, and we define the whole QMAC as being the tensor product of it. So we just apply one of these gates onto each different qubit. So if you apply this operator onto the quantum Fourier transformation of an integer itself, we will get this state here, which turns out to be just the quantum Fourier transformation of z plus y times x, which is the classical QMAC operation. So, since quantum Fourier transformation is a unitary operator, we can apply its adjoint operator and just recover z plus y times x. The problem here is that the M operator itself depends on y and x, which is something that we don't want to, because we cannot change our circuit which implements it every time we have different y's and different x's. So we need to decompose it to a more appropriate set of gates. We will use the phase shift gates and sub-circuit that's are composed of those. Like here. Just take different phase shift gates and we control them depending on a different bit of y. And since the phase shift gates we apply here will be identity if the bit itself is 0 and just themselves, if it's 1, we can just replace them with classical counter. So we'll use just single qubit quantum gates, which we counter classically on the different bits of y. And here I'm using 3 slashes to represent the multiplier bits of qubits, and this one dash to represent classical bits, and a bold line to represent quantum qubits. So we can make the subcircuit Q independent of y. Now we need to make the MJ subcircuits also independent of both y and x. So it is enough to show that can decompose it like this, and it's enough to show that this works. This holds true for the computational basis 0 and 1. So for 0, this works obviously because all of these Q's acting on 0 are just identity, act just as identity. So we start by looking at the definition of MJ. We expand X in binary format. Now we can use the definition of Q to write it as a set of QJ gates in a sequence. And now we note that the phase shift gates will be identity if the J will be less than 1, and that if we take it to the power of 2 to the power of m, it's just J minus m. So we can see what the operator Qj is if we take it to the power of 2 to the power of m. It happens to be Qj minus m. So we can just simplify the whole equation. We also note that the operator Qj itself will also be identity if J is less J minus m is less than 1. This comes from the fact that this was true for the R operators, and this allows us to remove some of these gates such that we get this kind of sequence of Qj operators. And since the bits of X that control it are just classical bits, and since the Q operator with argument 0 is the same as the Q operator to the power of 0, we can just multiply them in the argument. So now that we have the Q operators and the MJ operators independent of both X and Y, we can make them parallel. And this is just an extremely simple technique, well known, that if you use a fan-out operator and you want to apply diagonal gates, you can apply all of these diagonal gates simultaneously if you create the entangled state. So we can just take the gates that make up Q, initially create a fan-out state of the input to Q, and finally we just have to clean it up, applying it again. So this will parallelize the Q operator. And now, if you look at the definition of MJ, then the J times the bit of X can be computed using just a classical AND circuit, where we just multiply the bits of Y with one bit of X. So this gives us this parallel version of the MJ operator. Here we take the subcircuit of Q, the parallel version we saw in the last slide, and the value J, which is needed, we multiply with the appropriate bit from X, which we get by performing the classical AND. We move all of these fan-outs, which we needed to create, to apply the gates in parallel to the front and to the end. And with a bit of counting, we can see that this is just a bigger fan-out operator. And this is the parallel version of the MJ operator. Note that the depth of the MJ subcircuit is just 1. We need to perform one parallel AND and one application of QJ, which, as we saw from the last slide, is just one computational step. So now we take the MJ circuits and we put them into the definition of the M circuit. And we get the same structure, a similar structure, where we just have that the depth of the M prime will depend only on the depth of MJ subcircuits itself. So this would be our circuit, or QuantumMac circuit, if you would want to apply it in a sequence. So we have the initial quantum Fourier transformation, some M prime circuits with depth 2, and some fan-out operators in between. Note that because the fan-out operator is its own adjoint, two of them together give you identity, and hence most of the fan-out operators have no effect, and we can remove them from the circuit. So now we're left with the final circuit, and we can look at how many computational steps we need to actually apply it. So we have exactly n applications of M prime subcircuit, which has step 2. This gives us n. We also have that the fan-out operators can be decomposed into smaller 2-qubit gates, CNOT gates, with log k depth. This gives us an additional log k. And we have the quantum Fourier transformation, which can be done approximately in log k, or exactly in k steps. So in total, it will be n plus log k depth. And that is our final QuantumMac circuit applied in a sequence. So its features is that, well, it works on the relative phases of the quantum states, uses quantum Fourier transformation to initialize and read out. And we use a entangled state to apply the individual gates simultaneously. Well, small depth is useful if we want to apply it in reality, because it means we need to keep our state less time in a coherent state. Also, we use the fact that we could copy classical bits, something that quantumly you couldn't actually do with unbounded number. This also keeps the depth smaller. Also, using classical bits as control keeps the number of qubits small, because we're not representing all of the integers quantumly. Because we use them to control quantum gates, we don't also need many 2-qubit quantum gates. The bad thing is that we use a very entangled state, and keeping that coherent is difficult. And another bad thing is that the number of ancilla qubits, which we need to create these entangled states, that is very high. So yes, we created a new hybrid MAC, which outperforms the classical MAC circuit. And it's a useful computational pattern, since it's used in many different codes, computational codes. So this could be extended to work maybe on floating points, which would be more useful. Then we could try to find some hybrid circuits for other arithmetic operators, like for example division. We could try combine different arithmetic operations, see if a sequential application of different ones would give you some kind of benefit, since one application of this MAC wouldn't make any difference at all. And we could see if it would be reasonable to construct a quantum arithmetic logical unit. Would it give you any benefit to classical one? So, thank you for listening.
So, I think I have a question.
Yeah.
Do you have any proof that this is optimal, or there is
Optimal?
Or there is still
No.
some space for improvements?
I think I don't have a proof that this is optimal.
So we can expect some.
Let me think. Well, there's not much room of improvement. I mean, the steps themselves are constant, so you would want to improve the initialization or readout. Yeah, I don't have a proof that this is optimal.
Or you could get less than constant. I mean, you put in once a lot of numbers.
Yes, but this is possible. The thing is that if you have a lot of numbers, you would need a larger parallel circuit.
Yeah.
The most obvious way would be to just divide and conquer. You add and multiply half of them, half of them, half of them, half of them. This would give you the overall depth of log n. Yes, log n, exactly. Actually, log n times k. And that would be true for classical also. So this is useful only for a practical application where you actually don't have a possibility of creating a more parallel circuit if you have more...
Yeah, but what I'm saying is that perhaps there are other schemes that will not get that wide and that all still break the 4 of 1 long. I mean, you said the only thing that could be
Yes.
would be the 4 of log k.
Yes.
And it seems reasonable that you can't squeeze anything more in the O of 1 without boosting your...
So you mean that maybe there is
there's
something that also... Yeah, I see.
I don't think so.
I don't think so, yeah. I think if you get even lower than that, then you might get some results in the complexity theory for arithmetic circuits themselves. This here doesn't imply anything about in this sense. So, yeah.
Okay. Let's thank the speaker.